Hi guys, welcome. Today we're going to look at the secant method and we're going to use MATLAB for implementation. So, a brief overview of secant method. The secant method is another method of solving nonlinear equations, and it is said to be faster than the Newton's method. It is similar, but the Newton's method uses the tangent principle, while the secant method, it's in the name secant. So tangent is a line where it intersects with a graph at exactly one point, while the secant intersects a graph in 2 points. And in the secant method, it is said that the next approximation is the point where the secant line crosses the x-axis. So it's almost the same with the Newton's method, right? But in secant method, it uses the concept of similar triangles, and therefore secant method uses at least two initial guesses. Actually two initial guesses. And then we iterate until the number of iterations that we set, or reaching a tolerance. So let's begin. Let's switch screens. Okay. So here is our pseudocode for the secant method. Okay. So the parameters for this function are the function itself, xa, xb. So xa here is your first initial guess, and xb is your second initial guess, and then tolerance is the relative error that we desire, and nmax is the number of iterations that we desire, that we want. Okay. So now, let's code this thing. And I'm going to explain the code later. Okay, there. Okay, so what this function does is first we get the f of a and f of b. We're going to need these values for this formula here. So these three lines here, this d up to this x, this is actually the secant formula or the secant method. So this is actually x is equal to our xb, or our x sub I, minus our x sub I minus xi minus 1, that would be our xa, all over our f of x sub I, that's our fb here, fb minus fa, or our f of x sub I minus 1 multiplied by the f of x sub I. So that would be our fb here. Okay. So this is our second method. So we compute for this second method, then we evaluate a new y based on this x. Then we check for the approximate error. Then we compare if our approximate error is less than or equal to our relative error, or our tolerance. Then if it is true, then we end the loop, we end the algorithm. Then next, here we assign new values for the next iteration in case that the iteration is still going on. So our new xa, or our x sub I minus 1 is xb, our previous xb here. Then our new xb, the x sub I will be this new computed value here. Then our new f of a, our fa here, will be the one from the previous f of b, this one. Then, or rather, yeah, our previous f of b here, right? Then new fb, or new f of v, will be this one. Then it goes on until it reaches the maximum number of iterations that we set. Or this condition is true. If this condition is true, approximate error is less than or equal to the relative error or tolerance, then we end the algorithm. So the part here at the end, it's just printing. So we print using func2str for printing the original function. So this code here, func5 : end, this just removes this notation. Okay, I'll show it to you. This one. 1, 2, 3, 4, 5. So this func5 up to end truncates this part. The at x, this anonymous function notation. Okay. So now let's test this. Okay. So this is our test script here. So we have the function as x plus cosine of x, and our initial guesses is 0.5 for xi minus 1, x sub I minus 1, and our x sub I or xb here is 1. Then let's say we want a tolerance or relative error of 0.000001. 0, 0, 1 here. Then iterations is 10. So let's give this a try. Let's run this code. There. So we got the answer in 7 iterations. Okay. Now, what is the equivalent line command of this pseudocode in the script? So we assign b minus a, quantity b minus a all over quantity fb minus fa to d. So in this code, it's this part. It's this part. Similar, right? So initial guess x sub I minus initial guess x sub I minus 1, and this is our f of x sub I minus f of x sub I minus 1. So that's the equivalent. Next, suppose you entered the same arguments to Newton's method and secant method. Is there a significant error between the two of them? Let's find out. So let's call our Newton method here. Let's rename this. I got this wrong the last time. That's alright. When I filmed that one, it's already late at night. Method. Then we rename this function here. Just press fix. Save. Okay. Now going back, let's try running our Newton method. So for Newton method, we have f. X sub 0 would be 0.5. Let's also try with 1 later. Or x sub a rather. Tolerance, okay, let's just use the same tolerance. And our nmax. Oops. Okay. Let's run this code again. Where is our output? Oh, okay, because we used sims in the previous one. So let's rewrite this as sims so that it doesn't error out. Okay, so let's say fb, and this will be our sims x, the one with the sims x, symbolic math toolbox. Okay, let's remove this. Sims x. Then let's put fb here. There. Just to satisfy the requirements of the Newton method that we did in the previous video. So clear all, CLC. Let's rerun this. What happened? We don't have output. Oh, okay, because we didn't have output here. So let's uncomment this. Or rather, let's show the output of x. Okay, again, clear all, CLC, then we run. Okay, so it's similar. So however, here in the Newton method, it gets truncated into 4 decimal places. So I guess that is just the default for floating point values. Maybe when we try to run with y here being shown, the output being shown, let's see. Again, here all CLC SM_test. Okay, we have the same answer. However, how many iterations did the Newton method take? So, let's see. Okay. In order to see the, I did this in order to see the number of iterations for the Newton method. Again, clear all CLC for clean runtime. Okay. In this case, the number of iterations it took for secant method is 7 while here is 6. What's going on? Well, at least we got the same output. Almost the same. So the significant error is relatively low. Okay, next. What is the advantage of secant over the Newton's method in computer implementation? The advantage of secant method over the Newton's method is that the secant method uses 2 initial guesses instead of 1, so you have to evaluate 2 guesses at a time instead of 1 in the Newton's method. And also, the secant method is better for nonlinear equations that, or rather, where the derivative of such function is difficult to evaluate or find. So, I think that's all. So, to conclude, so we took an overview of the secant method, tried to implement it in MATLAB using loops and function evaluations. We passed a function, 2 initial guesses, tolerance, and maximum number of iterations. Then we computed iteratively with the secant formula, secant method. We check the approximate error, compare it with the tolerance. If it is equal or less than or equal to, we terminate the algorithm and we set values for the next iteration. Okay, then we tried to get the output of the secant method that we created here. Then we also tried to compare the results of the Newton method with the secant method. So there you have it. I hope you learned something. If you do, please like, share, and subscribe. And comment down below if you have a better implementation for this algorithm in MATLAB. So that's all for today, and I hope to see you on the next one. Have a good day. Bye for now.